Let's see if I'm live. What's our goal for today? We want to get n-beats algorithm working plus uncertainty measures. Wonderful. Boom. I need to update my stream, don't I? twitch.tv/dashboard. Let's write this. Using the n-beats algorithm to predict the price of Bitcoin. TensorFlow, time series, deep learning. Let's get rid of this. With TensorFlow. Boom. That can be the stream. Is that updated on the... I don't even know what this looks like on the homepage. This is how much of a Twitch novice I am. Will this just show me my... What do I look like? Okay, beautiful. There's some sort of ad there. I don't know how to get rid of that ad. But here we go. Lately I was watching the new Fast AI lecture series that's going down. Very good. Some very good information in this video about how to learn deep learning. So the meta learning around deep learning. So good video. But let's get into it. We've got a few things we're going to be doing today. Let me just tweet this stream out. What's the notification here? D-type error. Okay, beautiful. Let's get the Twitters open. By the way, this is not financial advice. Once again, we are getting some laggy Chrome windows. Stretching. I may have a plumber coming here soon. Let's write this down. Going live on Twitch. Using the n-beats algorithm. Far out. Algorithm to predict the price of Bitcoin. With TensorFlow. We'll put this deep learning time series with TensorFlow. Should I just put I'm going to put hashtag BTC here and see what happens. Yeah, because we get that colorful little warning. Time series forecasting with market prices is basically like palm reading. Let's try it anyway. HTTPS. Look at me like an absolute novice just typing out the full Twitch URL. Ashik, what's good, brother? Twitch.tv/Mr. Deberg. Is this going to load me? Why can't I get an emoji here? There we go. Tweet. Okay. Get out of Twitters. Ashik, you want to share the Twitch URL on the Discord for me, brother? That would be great. That way I can just get straight into coding. Okay. So let's see where we're at. We've got this notebook. Mind you, this notebook was nothing like 4 days ago. So we've come a long way. Thank you, Ashik. So today's the 27th of May. Let's update what we're doing so we have a little bit of a plan. 27th of May. TensorFlow windowing function, yes. Do we need it? Yes. We could always create our own. Yes, we are. We're also going to replicate and beats algorithm for BTC prices. We've got the code ready for that. We did that in a previous stream. So today we are, if you're joining in, we're predicting. Let's write the topic here. Topic. Predicting the price of Bitcoin with deep learning. Okay. Replicate MBEAT's algorithm for BTC prices, and then we are also going to look into get uncertainty estimates working. Okay, so let's just make sure our code is running. Thank you, Ashik. Appreciate it, my boy. We are up to here. So if I run this, it should all work. And if you want this notebook, it's already on GitHub. It won't, of course, have any of the changes that we have. For now, the notebook is on GitHub. So you can see it here, notebook. All this code should work. Alex, what's good, my friend? Welcome. Now, as I said, we may have an interruption at some point during this stream. I think a plumber might be coming to investigate some sort of roof leak at my place. So we will cross that bridge when it arrives, if it arrives. But today we're having some fun. We're playing. We're going to get the NBEAT's algorithm that we created in a few streams ago, working with our current code. Wonderful. So I actually got the multivariate time series working. So make a multivariate series. We have here the Bitcoin block reward. So we have two time series going on that we're trying to predict this value. So you notice there's a downward trend with the block reward and an upward trend in the price. So the theory here is that would the downward trend of the block reward contribute to the upward trend in the Bitcoin price? Hey, Blonded Az, what's good? I'm excellent, team. I'm very excited for today because we are making some headway in this notebook. Some very good headway. Look at that. We finally built a model. Okay. So the area in the milestone notebook, Ashik is saying that is with efficient at B0. Yeah, so TensorFlow 2.5.0 looks like it broke some things in the course, but nothing too outlandish, which is good. But we now have a model that beats the baseline. Look at this. Model 6 beats our baseline. As I said, it's very hard. With time series, it's very hard to beat a naive model, but we have done that. Well, actually, yeah, we have. Except our RMSE is lower on the naive model. So if we look back up at our evaluation metrics, RMSE predicts the mean. MAE will lead to forecasts of the median. So we have a model that beats our naive forecast on the MAE, not on the other metrics. So that's what we'll be looking to see if the NBeats algorithm works. Let's see what our TensorFlow windows do. I was testing it with and without the block reward to see what it does. So if we train this here for 500 epochs, this should actually be 100. We'll upgrade the number of epochs it's training with after. We haven't even switched on a GPU, by the way. So this is one of the benefits of time series data, is that it's quite small. Our training samples are only about 2,000, so they run pretty quick on CPU. We will use a GPU after we get the NBeats algorithm working. So let's get this paper. Going to click that. Okay, let's see our NBeats algorithm. Let's see if this have I got the forecasting is BS? Okay, wonderful. Arthuro, hello everyone. CS50X, what's the difference between CS50 and CS50X? Let's look this up. CS50X. Oh. Beautiful. Great idea going back to basics. CS50 is, I highly recommend that. But let's get this algorithm working, and then we can go back and clean up the code later. So this is what we want to replicate. We've already done this, so we're not going to be diving too much into it. We're basically going to be copying this to where we need it. So this is the algorithm where we're going to use. Way too zoomed in. So this is the algorithm. And in a previous stream, you can look this up on my archive channel. We replicated this, and this is what we have here. So let's just bring it in. All this is a block. So we have a number of hidden layers here, which is going to be a fully connected layer times 4. It splits it into 2 fully connected layers and has a backcast and a forecast. The backcast looks to predict backwards on the time horizon, and the forecast, of course, predicts on the forecast horizon. Then we have some skip connections here. We subtract the backcast, but we add the forecast together. So this is what they found works best in combination here. And then they have some sort of ensembling, but we will get into that later. So I want to put that here. All right, just write this down here. We've got notes everywhere. To do, does ensembling with different loss functions lead to some kind of pseudo uncertainty. All right, so we're going to know pretty quickly whether this works or not. So let's just copy this over. Rather than copy and paste it, I'm going to rewrite it. So we'll create the nbeats block. Now all we had to do with this was we just had to make this block a custom layer, and then we can build this stack input using the functional API. So that was the easiest setup that I found. So class nbeats block tf_kerrers layers.layer. So we're subclassing the layer class of TensorFlow. With every subclass of a layer or subclass in Python, you need to init it. So init, this will take a while to learn. Like I'm still learning it as well. You just need to know this syntax. The input size is going to be an int. The theta size is going to be an int. Horizon is how far we're predicting. We'll probably clean up these variables as well, but these are just the original. N neurons is going to be the number of hidden units in our dense layers. N layers is going to be the number of layers in a block. And for the paper, they use 4. And if you want the hyperparameters of this paper, it is in section 18, I believe. I'll just write this here. Build model and hyperparameters for nbeats paper available in section 18. So this is, if I've done everything right, this is actually a pretty smooth implementation of the generic version of the nbeats algorithm. So is section 18 here? What if I just searched 18? Hyperparameters. No, appendix D. There we go. Hyperparameter settings. Beautiful. Are available. I'm not sure where I got section 18 from, but let's just write this. Appendix D. Okay, so we're going to continue making this block. Once we've initted it, in TensorFlow, you can also put keyword args here that will help with a bunch of things that you would usually input to layers, such as I think like input shape. Then we're going to init it with super. I really couldn't explain to you what super does. Maybe if someone has a good guide of what super is, I would have to look up. When I was first learning object-oriented, this confused me like hell. Like you have an init function and then you have a super.init, and it's just like, why are we doing this twice? I don't know, but that's apparently how it's done. Then we have input size. We're going to set up the variables. This is the, I think it's the, is this called the constructor? Am I using that terminology right? Constructor or initializer? Someone correct my terminology, please, for Python classes. Then we got to go self.nneurons. Hey, Maxwell, what's good? Supernova, welcome, welcome, welcome. Hey, Elks N Jr. I'm trying to pronounce your name. Alexander Jr. There's not many vowels in your name. But which deep learning book do you recommend to beginners? So if you look up Daniel Burke machine learning books, I recommend all of these. This.
Reading is learning. And as you'll see in this video,
there's me looking like a news presenter telling you about Machine Learning Monthly is going great. We are, I haven't made this month's yet, but I have a bunch of resources ready for it. So let's get back to this. Otherwise, for books for deep learning, hands-on machine learning with scikit-learn and TensorFlow, very much recommend that. Deep learning for coders with FastAI and PyTorch, also recommend that. My advice is to just pick one book. They're all pretty good these days, and just go through it, read it end to end, and then go back and practice the parts which stood out to you. Another one is Deep Learning with Python by Francois Chalet, which is he's the author of Keras. I recommend that as well. Self.hidden. Maybe I do an updated version of my deep learning books. Video. Activation equals relu. Okay, so here's where we're getting into the crux of the block layer. Is we're creating just a list of layers here, right? Because this, why did I get out of that? We'll get that hyperparameters later. Figure 1. Because this is just a fully connected stack, right? So we can stack together 4 dense layers. So we're just going to have a list here, a list comprehension, which is going to stack together a number of layers in a range n layers. So this is where n layers comes from. Beautiful. So there's our hidden. Then we can create a theta layer, which is going to be a dense layer with a linear activation. Self.theta layer. And if you want to know where I'm getting like activation equals relu for these dense layers, again, that's mentioned in the paper. We've talked about this in a previous stream, so I'm not going to go back through that for now. Otherwise, we'll just be reinventing the wheel. Dense, theta size, activation equals linear. Again, this is another thing that's in the paper. And we're going to give this a name equals theta. Maybe we could give these names too. Nah, we don't need to. Okay, and then if you're subclassing TensorFlow layer, Keras layer class, you need to implement the call method. Why? Because the call method is going to, let's see if we can demonstrate this actually. But essentially the call method is when you call the nbeats block in a model architecture, it's going to run the call method. So we need to have a call method implemented. So if I run a model up here, maybe this will show us an example of the call method. So let's just rerun this. Are we going to get... Oh, it's too many things down here. So somewhere in there, there's a call method. Yeah, call. You can see call. That's right down the bottom of the screen, but you can see there's a call method there. So when we call fit, it's going to run through these layers and find the call method within inside that layer, and then it will run. So let's see if we can actually find this. Let's look up the TensorFlow dense layer. TensorFlow dense layer. Best resource to learn Python classes. Real Python is probably my favorite resource for learning Python things. And then of course, just writing code and practicing it. Just seeing how it's implemented elsewhere. Do we have the source on GitHub? Let's see if we can find an example of the call method. So you see here, dense is going to inherit from layer, and Then we have a build method. That's another thing that we could implement, but it has a call method, right? So this is actually this is the TensorFlow dense layer, so it's got a lot more stuff than what we have. Ah, there we go. That'll be an example of our get config. Let me just example here. Wonderful. Okay, let's get back to where we were. So yeah, the call method is just, it's going to run when we run the cell. And what do we want to do? So we're going to create a copy of inputs so that we can manipulate the inputs. And then we're going to go for layer. So see how we created this list comprehension of layer? So for each layer in the hidden, so self.hidden, we're going to pass x, which is just the inputs. The inputs to our model are going to be are going to be some kind of time series, as we see up here, which is just going to be values over time. In our case, it's going to be windows of values. So it's going to take the inputs of the windows, it's going to compute on those after we've passed it through each of the fully connected layers. So that's what we've done here. Using our list comprehension, we pass it through the fully connected stack. After we pass it through the fully connected stack, we need to create theta. Theta is going to be our theta layer, which we take x here. We've just reassigned x to, it's going to reassign itself every time it passes through a layer in our fully connected stack. Theta is here. And then the backcast is, of course, going to be this part. We want the backwards cast, so it's going to try and predict backwards as well as forwards. So it's kind of like that kind of sounds like a bidirectional LSTM to me. But it's not, this is just a dense layer. So we're going to siphon off the backwards pass as well as the forward pass. And we can do that by implementing this forecast equals theta. So we're going to take the self. Now we have to check here. I want to make sure, are these the right dimensions? We'll find this out when we run our model. Self dot input size, and then we have theta here. Good morning, Sarav, welcome. And someone said before, I believe it might have been Elks and Dr. Jr. I've said that like 4 different ways. I hope these streams never end. Yeah, I plan on doing a lot more streams, so stay tuned. Some very exciting things coming up. Some fun streams, some building streams, some educational streams. That way we can all learn together. Okay, wonderful. So now we should have an mbeats block. Let's try to see if we can create mbeats. Let's implement this block layer equals mbeats block. Now here's where we want to fix up our parameters. So I believe I've implemented the parameters here. So the look back is actually going to be our window size. Window size. Now they used a look back, an input size of look back times the horizon. So I don't think I'm going to do that. We can experiment with this later, but let's just here instantiate input variables. Window size is going to be 7. Horizon equals 1. How far to look back. And this is how far to predict forward. So essentially what we're doing here, because we're trying to predict the price of Bitcoin, we have the price of Bitcoin from day to day. We are going to use a week to look back. So we want to use I was looking at this Logitech camera. We're going to use a week worth of Bitcoin prices to try and predict to the next day. As we'll see, that's actually very hard to do. And again, it's kind of like palm reading. That was the warning. Time series prediction in an open system is kind of like palm reading. So n stacks equals 30. These are values from the paper, so I'm not going to go through those. Values from paper. See figure 1/appendix D. N stacks. And then the input size, again, they use the look back times the horizon, so that would be the window size times the horizon. So the inputs, our model would then take windows of... So maybe I might just try... No, that's not what we can do. We can do the input size... Workout and cooking streams. Oh, that'd be cool as well. So the input size, let's see what we can do with this. So the window size plus the horizon. So that means we're going to have to create, let's just write this down, to do create appropriately sized inputs for n beats. Windowing function. We might have to do that in a second, but we'll cross that bridge when it comes. Theta size equals input, input size plus horizon. So what is that going to give us? Theta size. Input size, theta size. 8, 9. Okay, so that's... That's not what we want. Or actually, let's just use the values from the paper. Why not? Well, rather than theorizing anything, let's just create what we need to create. So the input size is going to equal input size. Maybe these should all be capitals. That way we're not getting confused. You came 7th in a KO competition? That's amazing. Congratulations, Sarav. Input size. And then theta size. Okay, this will help us not get confused. Beautiful. Okay, let's set up this. Now we've got custom variables, input size, what's the next variable? Theta size. And then horizon equals horizon. And neurons equals, and neurons, and layers equals n layers. Okay, now we have an n beats block. Okay, and so it should take some form of input. So in our case, let's create dummy inputs equals tf range 8. Dummy inputs, what's this going to be? Let's do dummy inputs. Okay, there we go. So if we pass this through and beats, let's see what happens when we try to pass the dummy input. So this is just a range, like this would be our window. That's what we want to pass it through. N beats block, layer, dummy inputs. Does this work? No. We need there we go. Maybe we expand it on, because if we have a look at okay, there we go. So we get a backcast and we get a forecast. Wonderful. So our NBeaks block is working. But of course it is. We'd already figured that out, haven't we, team? Okay. Now, let's combine it into a model and fit it. And then we can test where it's going wrong. So build the number of stacks. Input size equals input size. It's actually some beautifully written code. Yeah, so this is what I wasn't quite sure about with the yeah, so X is the backcast and Y is the forwardcast. So this is our double residual stacking that we're doing. This is going to look out absolutely outstanding. Let's have a look at this. Okay. Well, we've already got the initial block. Let's just put this as here. Name equals initial block. So we've already got num stacks. Yes, we do. So the stack model input is going to be, we're going to use the functional API for this. Shape is going to be the input size, which is actually in capitals now, isn't it? Shape is going to be the input size. Now, of course, the input size is what? It's window size times horizon. Yeah, well, we're using a horizon of 1, so that makes sense. Input size, and then name here is going to be stack input. Residuals and the forecast is going to be n beats block layer. we're going to pass it in the stack input. Then we're going to take these and create initial, backcast, and forecast input. Create stacks of blocks. So for I boom in enumerate range num stacks -1, because we've already got a stack at the start. Let's now create backcast block forecast equals nbeats block. Let's go into here, we'll initialize our nbeats block. I think this is actually all right. We don't have to change many of the variables here. Input size, theta size. Of course, we will see if this works with our data, won't we? Empirically, we will find out. Horizon equals horizon. And neurons equals, we're cooks, not chemists. People, cooks, not chemists. N layers equals n layers. And we're going to give it a name. Name can be F. We'll format this with the enumerated I. Mbeats block I. And we're going to pass it in residuals. Pass it in the backcast. So yeah, if we see this, this is again reflective of the block layer, is that the residuals are going to go into the block and the stack forecasts are going to get added up. So this is the double residual stacking. So this is where we now have to bring in our residuals. So residuals is, in time series forecasting, residuals is a name for the backcast, the actual values, actual backcast values minus the predicted values. So that's why they're called residuals here. So residuals is going to be a subtract layer, layers.subtract. Let's have a little query of what this actually does. TF Keras layers. Just to make sure we're on the right track, you know? Subtract. Difference of the inputs. Okay, so let's just implement this and just see if we can get it to work. I'll give this a little link. Subtract layer, TF, oh, we'll just do layers.subtract, won't we? Layers.subtract. X1, X2, X1 equals TF range 10 equals TF range 10 plus 10. Layers.subtract. Do we need a list? Yeah. X1, X2. And then subtract. Oh, we need to create 2 inputs. Let's just see if we can replicate this. And then the things we go for demos. It's all practice, right? It is all practice. There we go. Yeah, so it just subtracts one tensor from another. That was a lot of code for a demo. Demo the subtract layer. And then the same will be for add. Yeah, so then we're setting up the backcast here, and the residuals are going to be, so this is constantly looping back on itself. This is the residual connections. Quite confusing when you first read it, but then when we plot the model, we'll start to see where the connections are coming from. That's how we'll verify that our architecture is correct to the best of my knowledge. Of course, there may be something a little bit wrong, but I'll leave that for you guys to figure out. Forecast equals block forecast, and I'm going to call this name equals f add layer. Throw in a little I there, and then we'll put it all together into a stack model equals tf chars model. Inputs is going to be stack input, and then the outputs is going to be the forecast. Name equals stack model. Num stacks is not defined, and stacks. Spelling subtract wrong everywhere. Wonderful. Now I'll come back in a second and we're going to plot this model. Back soon. Who know what? Who knows what time it is? That was a fail. It is San Pellegrino time. We have a drink. And it's going to be a very exciting couple of code cells that we're about to run, because we get to, first of all, plot our model. Second of all, we get to see if the n-beats algorithm works on our Bitcoin data. We should have a mimosa stream. I never tried drunk coding. There's probably a reason for that. This is San Pellegrino. Sparkling water. A little bit fancy. Nah, just San Pellegrino. There's a little bit of orange juice in here. Ubido is keen to watch a drunk coding Twitch set. It would probably turn out to be an absolute mess. I get distracted enough when I'm sober. Okay, so now let's have a look at our stack model layers. As we'll see, it's quite a large model. Boom. Right? So, again, these are just the hyperparameters we've taken from the paper. And now let's plot it. So from Keras utils, import plot model, and we're going to plot model our stack model. So this is a very big plot. Oh, what's happened? From TensorFlow, Keras. Oh. Boom. So now we see our residual outputs. Magnifique. I wonder if we could get away without using the initial block. But then we wouldn't have residuals. So this is our residual connection. This part here is this part here. And this part here is this part here. And then they all get combined to equal the final forecast. Add, boom, forecast. Wonderful. So now let's try this on some data. So on stack model, we need to compile. We'll get it to just do the same loss function and the same optimizer we've been using so far. Let's full screen this so it's easy to see. Then we will also fit. Stack model.fit. What is our training data currently? It might work just on that. Let's just see what happens if we fit it on that. What's it expecting as input size? Yeah, that might work. Validation data can be test data set. And then we will also add a callback. Let's see if this works. We might need a GPU for this one. Oh, ladies and gentlemen, we are fitting the NB's algorithm to our data. Look at that. What a thing of beauty. So this takes 26 seconds per epoch. And it's going to take quite a while to save it, isn't it? Yeah. Oh, this is quite cool. Okay, so the validation loss is going up. So the loss starts out quite small, but then increases as it gets to the tail end of the epochs. So that's making me think that the loss is bigger as the Bitcoin price goes up. Okay, validation loss is increasing here. Yeah, so the loss starts quite small. Oh, we're getting a loss decline here. So the loss for the initial training oh, loss is declining. This is good. Might need a GPU for this though. We're getting a lot of warnings here because we haven't implemented a config. So what I'm going to do is I'll get a GPU working. And then I'm also going to start adjusting some of the parameters here. I'll maybe increase the batch size. Yeah, that's what I think I'll do. Oh, so we've got another loss decline. This is good. Let me write this down next. We'll just watch this one finish off. Hey, shall we? Get GPU working. NBeats is an intense algorithm. Fiddle around with batch size. Does this affect the model much? Okay, so the lowest loss we get there is 611. All right, let's get a GPU. But let's save this. Let's see how much a GPU increases our speed. So we're looking at about 18 seconds per epoch with no GPU. So this should run pretty quickly. I'm going to increase the batch size too. Yeah, so there was call. That's where we see call. Call, 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 call. Fit, call, 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 call. That's why we have to implement call when we're creating a custom layer. So the biggest bottleneck here was loading the data onto the GPU. That was for our conv1D model. LSTM model. Yeah, so these fit incredibly quick. Look at that, a millisecond. But the loss fluctuates something fierce. So I've just increased the batch size to 128. Let's see what happens when we fit this now with a larger batch size. So before we were getting about 18 seconds per epoch. So the first one took the longest, of course, 8 seconds. So that's going to save the model. And we get a 1 second time for the next one. Yeah, okay, so with the GPU, we get some ridiculous speed ups. It does take a while to save the model though. Yeah, that's how much of a speed up we get. Let's train this for 100 epochs with a batch size of I wonder if we go let's check out the model checkpoint. I might just use an early stopping callback. That'll probably be better. So if it doesn't improve for 20 epochs, and I'm going to restore the best weights equals true. So this should be pretty quick. Much better. And then it stopped there. Did it restore the best weights? Yes, it did. 610. What if we change the batch size to 32? I think we needed to obey the learning rate scaling. If we're going to use a higher batch size, we need to lower the learning rate. Linear learning rate scaling rule. Here we go. Increase the learning rate by k times, where k is the times your batch size is increased. Okay. So if we increase the, what were the naive results? Does this beat it yet? Let's see what happens when we obey the linear learning rate scaling rule. What did the paper say? We use the Atom optimizer with default settings and initial learning rate 0.1. Scaling? What do they use? for the learning rate. NBeats is implemented trained in TensorFlow. Let's see what happens with this. We get some wild results here. Oh, it's exploded. Learning rate way too high. Let's divide it by 4. Much better. Hey, look at that. Looks like we're overfitting a bit. So I wonder if we set the batch size. I need to fix up this code so we're not scrolling all the way back up here. 32, and we lower the learning rate. You can use the early stopping callback whenever you want. Let's have a look at some other callbacks. Learning rate scheduler, reduce LR on plateau. There we go. So yeah, it's actually quite hard, as we see here, to beat the naive model. But what happens if we start here, and then we add a reduce on plateau callback? Patience, I'm going to let it go for 50 epochs. And callbacks, let's bring in some reduce LR on plateau. Give me a doc string. Come on. We'll divide it by 10. Patience equals 20. And that can be it. And we'll train for 500 epochs. Batch size of 1024. Wow. Do they use learning rate decay though? I need to get rid of some extra tabs. Oh yeah, it definitely does fluctuate too much to begin with. But then it kind of gets stuck in this. See, they use a batch size of 1024. What happens if we increase our batch size to 1024? I'm just going to make batch size Wonder if we shouldn't run out of GPU memory. You reckon it's going to go out of memory? Well, let's find out. Boom. I think our algorithm maxes out at like we're using a different data set than the paper. Yeah, see, it gets stuck. We might be overfitting. It looks like we're definitely overfitting. Good news is that it fits quite fast, so it doesn't really matter. Himusak Imagoro asks, is there any way to merge collabs together? No, there is not, or not that I know of. What if we optimize for RMSE? What, there's no loss function? Yeah, I wonder if we optimize for MSE, what happens. They optimize for multiple losses in here. The early stopping and the number of batches is determined on the validation data set. They just said the batches. So let's create a data set here that's going to help us. What's happened here? I want to create a data function here that's going to allow us to wonder if I do 30. I haven't got any great results yet with the n-beats algorithm. Nothing too much different to what we've already got. We've got some duplicate code here, but that's okay because we're gonna I might shift this into its own notebook. I got some pretty good GPUs here in Australia. Yeah, look, I got a T4. See you later, Ubido. Thank you for joining in. Here we go. We're training with a larger window. Okay, we got a lot of stuff everywhere, so let's clean this up. So we're running into some errors here. So I think if we run this... Okay, it's going to get an input size there. I'm not sure what happened here. So this was working. Oops, sorry team. So we'll clean this up, as we always say, later on, but let's get it back to working. This is very strange. Oh, we have nans. Did you catch that? Derp. Classic. Always check the inputs to your models. Did we run out of memory? Pausing. .001. Okay, here we go. We're back online, team. Well, at least we got it working. But with all that effort, our n-beats model still doesn't beat our baseline. So let's tweak a few things again. I wonder if we kept going, would it eventually get there? They use a batch size of 1024. We're using that. They use the default atom. Let's increase the window size. Oh my goodness. So I think our Windows sweet spot is around a week. Otherwise, our model's going too far back. Yeah, I think our Windows sweet spot's about a week. I've just lowered the number of hidden units. It's now 128 instead of 512. Okay, wow. 512 gets pretty good results. But this is a lot more constant now. Watching the validation loss, by the way. How many iterations did they train for? daily 5,000. Let's just replicate what they have. And they optimize on SMAP. I wonder what happens when we optimize on MAPE. So we're replicating this with the paper settings now. They ran it for 5,000 iterations. And that's what we're running it for. Okay, so it's going to stop relatively soon. There we go. So all that work, and we just beat the naive result. Have a go at that. We just beat the naive results with NBeat's algorithm. Now let's try to minimize on MAPE. Okay, we're going to get a convergence pretty quickly. Now let's try MSE. What other losses are there? So Huber loss is a combination of MAE and MSE. Wonder what happens if we shuffle our training data. Oh, Huber loss looks like the best so far. For MAE, that is. Now, I wonder if we shuffle the training data, what happens? Akash says, I want to ask, if we have less time series data, how can we create artificial data? I'm starting a project, but data is very less. Can you expand on that, please? You mean like data augmentation for time series data? Time series, you're generally going to have a lot less data than, depending on the frequency of your time series. Boom. Yes, okay. So it looks like Huber loss is the best. After 165 epochs. I'd be very careful if you're trying to... Hold on. I might need to move this. Yeah, I'd be very careful if you're trying to create extra data for time series, because any method that you create data will probably not be from the distribution that you want to model. Are we using the right batch size here? It's still going. Okay, I think we've done enough here. Now let's see. Oh yeah, time series is very complex. Should we ensemble? What's most important to do next? We've done that. This is what we've done. We're replicating the n-beats algorithm for BTC prices, yes. N-beats. Now let's... Yeah, let's use different loss functions and plot the prediction intervals. How does this look? Okay. So I think still our best results are nearly model 1. I think with the tricks that we've done for n-beats, we can get nearly the same results as n-beats as just with model 1. Yeah, a cache. You can create it randomly, or you can just create it similar to the existing data that you have. There's a number of different ways to create artificial data. I just start by searching artificial time series data. There we go. Creating synthetic time series data. Try a couple of tricks for a simple model. Simple model. Like all the fanciness we get of n beats, we can basically almost replicate by just having a single layer model. So we end up getting just below naive model results with a fairly simple model. Wonder if we put dropout in here. What did they say about dropout in here? Yeah, so they find ensembling better than dropout. So let's build an ensemble. If we're getting pretty close to n beats results using a simple model, let's take that and we'll ensemble them across Bytewiser, why are you trying NBeats? Because NBeats is the state of the art for time series univariate models. Yeah, we focus on solving the univariate time series point forecasting problem using deep learning. Okay, let's see if we can improve our results using ensemble. Create an ensemble. We're going to do 3 versions of simple model. MAE, MSE, MAPE. Don't bother with it. Solve the problem after it has been solved. What do you mean? They already knew the results when they created NBeats. Can you expand? Um, What the far out? Is that the type of data structure that we want? Do we want a dictionary? Let's just see what happens. Beautiful. How do you extract just the values from a dictionary? Can you do it without dict.values? There we go. Typos galore. We'll turn it into a list first. What is happening here? We'll get this into an MP array then. I can't turn this into a constant, a TF Why can't I turn this into a constant? I have to go list into an array into a constant. Wow. In that case, I'll just use NumPy. Does MP mean have an axis value? Oh, there we go. Now the ensemble still doesn't get better than the naive results. Would you look at that? DevZoo says, with data science, can you use it to scan pictures to find certain details? I thought that would be machine learning. Really depends what kind of details you're looking for. I mean, data science and machine learning, the lines are blurred because machine learning is a part of data science. So I often use the terms interchangeably. Now let's get ensemble preds. Does TensorFlow have a variance? Beautiful. So here's how much our predictions vary. Preview of my data science course. Where was that? What are you confused about? How can I help? Now, I wonder how we can plot these. So if you're confused, you can also see that link. This should help on what you learn there. So here's what you'll learn. You'll learn Python because you write data science code in Python. You'll learn how to analyze data in pandas. You'll learn how to visualize data using matplotlib. You'll be able to write machine learning algorithms using sklearn. You'll also learn what machine learning can be used for, so you get an idea of different problems that machine learning is good for. If you're still stuck, I would encourage you to go through my ML roadmap. This is a big video, but
If you were to try and code up all these...
it'll be worth your time. Okay, now let's figure out, plot the variance of ensemble preds to view the range at which different... We'll just plot the variance of the ensemble preds, hey? No need to apologize, my friend. That's what the chat is for, asking questions. I'm on the Korean version of TensorFlow. Never apologize for having the balls to ask a question. I'm on the Korean. Okay, how do we plot variance? Oh, how long have we been going for? Only 3 hours. Exciting. Plot variance matplotlib. error bars. Wonderful. Oh, this might look... There we go. That's what we want. Something like that. How cool is that? Okay. Plotting the variance So hopefully this variance is going to give us our prediction interval. Define the model to draw some data. Should we just write this out so we can get a feel for it? This is a beautifully created website too. I want to create a website like this. The plumber hasn't shown up yet. I know, classic. Let's just rewrite this code and see if we can get used to it. Fit the Gaussian process model. Maybe Seaborn will help us. Hey, Dev Zeus, thank you for the subscription. Here we go. Oh, yes. Ladies and gentlemen, we can also see here. We're just going to copy this code out here so we can get a feel for it. So X, we're going to create some lin space. Y, we're creating a sine curve. really like to get a feel for things rather than just... Alright, I'm cooking dinner tonight for the family. I'm really excited, actually. I just realized that. It's Thursday, team. We've had a good stream so far. We're getting very close to having the baseline materials ready for this notebook. I really need to include error bars in this because uncertainty predictions. I'm kind of going to use the prediction intervals as pseudo uncertainty. What's K? What if I just did this? Then we use the fill between method. X, Y minus error. Yes, the plus or minus. Y plus error. Cooking steak tonight, Ashik. That's what we want. Okay, so that's something that we want for our plot. So let's see. Plot example of prediction intervals. Now let's plot variance of our ensemble preds. So we've actually already got this. Okay, so we can plot our ensemble preds. Friends, I think we may be closer than we think to this. So we're going to plot the mean. Should we plot the mean or the median? What gives us better values? Better results? Oh, the median does. Slightly better than the naive. Wonderful. So if we plot the median... Let's do that. Plot.figure. Friends, this is going to be so exciting. Plt.plot, xtest. Let's just create the... Plot the variance / median. So ensemble med equals NP median. Does TensorFlow have a reduced median? Why does TensorFlow not have a median? Doesn't matter. Oh, wow. I think I screwed up the... Oh no, that should be correct. That's not correct. Will this work? Boom. Watch this. Cass, I listened to. Did you send through the George Hotz one where he was talking to? I can't remember who he was talking to actually, but he was talking about comma and just Tesla, etc., etc. Just a whole bunch of normal George Hotz topics. I really like that one. Why we want ensemble median. We're going to minus the variance. Why don't we have ensemble var? I'm a big fan of George Hotz. I did start listening to the ML Street Talk with Francois Chalet, but the start kind of tripped me out because it was just talking about a whole bunch of things that I didn't really get. So, is this going to work? Oh my gosh. What happened? Do I need to log back in? Yeah, I haven't started listening. Let me show you. Someone sent it through yesterday, I think. This one. I really liked that one. I think I need to relog back into Google Chrome. So I need one of those stream buttons. Who knows what the button is for the stream thing to just change windows? There we go. Now, how do I log back into YouTube without this being broadcast everywhere? Minimize. Let me just here. There we go. I'm just going to log back into Chrome without this being streamed. I think that's what wrecked everything. Is this what's coming up on Twitch right now? Just me, half the screen? Yes, beautiful. That's what I want. Who knows more about Twitch than me? And I think there's like a piece of hardware that you can get that will automatically change scenes. There we go. Boom. Logged back in. Sign in. I've already signed in, man. Rumor has it that if you get logged out of Google Chrome while you're on it, did I just lose everything? And we're back. Hello, friends. Yeah, I think there's, unstable deuce. I think you're right. Might be a streamcaster of some sort. What did we get wrong here? Yes, that's what I'd like to plot. Why is that negative? That can't be right. Negative 17,000. Stream Deck. That's what we want. Okay. Yeah, I think that's what we want. So then I could just go boom, hide Windows, and then it's just blank. Okay. And what if we got... What's going on here? Wow, there's some value which has a variance of 90,000. What error are we getting? Wow, friends, look at this. The variance in our preds. Boom. This is what's up. Look at that. We get a dramatic amount of variance here. How cool is that? So does this make sense? The lower the price of Bitcoin, the less variance, but then the closer we get to the higher the price, the more the variance of our predictions. So that means our predictions aren't very trustworthy, right? Well, if it could be with between 150,000 and negative 25,000, this is beautiful. This is what we wanted the whole time. Now let's zoom in a little. This makes sense. Boom. Look at that. We've come a very long way. We just got uncertainty measurements. Plot. Let's bring in this. Can I give this a label? How do I get the legend on the left? Look at that. Look at that, team. Your error bars are as important as your actual prediction. So the predictions follow the line pretty well. However, they have a great deal of variance. Haha, that's very cool. Okay. So that's what you have to be careful of. So your model could say one thing, but look how big that variance is. We now have, is it called alloteric uncertainty? This is subway uncertainty. Next, we have to make future forecasts. Let's do that. I'm not going to experiment with different window sizes. A week is enough. So, okay. That is very cool. I'm very happy with that. Uncertainty plotting. Look at that. We did that. Uncertainty plotting. We have done that. Compare all models. Let's get rid of that. We have subway uncertainty. So this prediction point here is saying it could be $150,000 or it could be negative 25,000. So I've used different loss functions to figure out some form of uncertainty or to simulate uncertainty. Get uncertainty estimates working. We're not going to run through multiple window sizes. That can be an extension. TensorFlow windowing function. We could probably still come back to that. Let's now get rid of that. And now, next is make future forecasts, plot the uncertainty with each of these. So make a forecast of 1, add it to the buffer, forecast of 1, add it to the buffer, etc., etc. See how our model performs on the latest Bitcoin data. To make predictions with a time series model, you have to retrain a model every time, e.g. updated daily. You need to retrain your model every day with new data for new predictions. Okay. And then, of course, we need to, once again, I think this notebook will be finished tomorrow. Clean up code. Make it tidy and simple and runnable. Yeah. And then turkey problem. That'll be great. Turkey problem. show where time series models will buckle. Insert an outlandish Aircoin price increase drop and show how the model fails. Something to be wary of in your own problems. Okay. So I think we are... Look at this, friends. We've just done uncertainty estimates. We're going to clean that up later. Next is making future forecasts and plotting them. We've got a way to make uncertainty forecasts here. So it would also be good that if we did bring out a prediction estimate, we'd have plus or minus a certain value. But that's how we know we've got some sort of uncertainty estimate here. Yeah. Let's see if this looks like Uber uncertainty estimate. I'm going to go to the gym after this. I'm that excited. So does our plot look something like what Uber's plot looks like? Yes, it does. See, they use all of these fancy algorithms and stuff like that. Boom. This is what we want. That's what we want. We want those waves. Okay, beautiful. So we're getting somewhere towards simulated uncertainty. So let's add this to the GitHub. If you want this, it'll all be on GitHub. Add NBeats. This has been a productive coding session. What have I been going for? Nearly 3.5 hours. Add NBeats model plus ensemble model plus uncertainty prediction intervals. And if you want the notebook, it's going to be here in a minute. There we go. Boom. Notebook for the stream is here. So that'll be on GitHub, TensorFlow Deep Learning, and it is number 10. But tomorrow we will be back and we will keep going with where we're up to. Thank you all for tuning in. Wherever you are, keep learning, keep moving. I'm about to go to the gym and have a fun time. Get my body moving. I've been sitting down for too long. But I'll see you all next time. Peace.